Security Data Analytics and Visualization. Number 7, Text Analytics. As a primary form of communication, the written or spoken word provides a massive wealth of information for many applications. For the most part, we've been dealing with numerical data so far, yet there are plenty of applications where we'd want to examine text rather than numerical data. For example, email analysis, social media analysis, product reviews, legalese, document classification, and many more. Natural language processing, NLP, is a subject area in its own right, but for now, we will introduce the topic and explore some of the methods that could be used for security analysis. What kinds of processing may we want to achieve? We may want natural language generation, for example, creating a chatbot that can respond to user questions, topic modelling, classification of document types, sentiment analysis, understanding emotional traits, text clustering, relationship between words, named entity recognition, for example, what are the things mentioned in a sentence, such as the blue car drove down the road. We may also want to identify keywords of interest from a large text corpus. We can use a method known as term frequency inverse document frequency, which we will discuss shortly. How do text analytics relate to security needs? We may want to examine user emotion through their use of language, common in psychological assessment, such as insider threat detection. We may want to classify conversations or news articles, especially given the wealth of text information online and how rapidly new content appears through social media sites and the like. We may also want to authenticate users based on their language or observe when language may change. This could be in part of identifying if information is genuine or if an attempt is made to falsify information from a given source. The rise of fake news on social media makes this an important security issue related to how we trust and scrutinize online materials. As alluded to earlier, humans are excellent at understanding language. However, computers are not. Therefore, we need to establish models that operate in similar ways to how we understand and interpret language, recognizing that these will be limited in their performance, but that they are much more scalable than human resource, leaving humans to then verify the outcomes of the model. Word occurrences. A simple approach to begin with would be to examine the occurrence or count of each unique word within a document. This example takes the computer security Wikipedia article and assesses the number of times each word appears on the page to develop a topic model. As we may expect, security is the most used word in the article. However, we can learn some other useful information from this, such as cyber, information, network, and systems also occurring frequently. This essentially allows us to build a dictionary of related terms that could be used to connect topics together. This concept of measuring word occurrences is often referred to as a bag of words model. We can use this same approach to assess how frequently a given word or set of words occur within some text or a set of documents. Whilst this sounds fairly simple, it is also very effective. It is essentially how password brute forcing works. Take the RockU dataset of 14 million passwords, for example, and scan a set of web pages to see if these dictionary terms occur, and you could potentially identify websites that are based on weak credentials. This opens up a range of possibilities in the scope of open source intelligence, how to gather and analyze information that is openly available online. Other uses may explore dictionaries such as the Linguistic Inquiry Word Count, LIWC, that is popular in psychology and can be used to identify positive and negative sentiment along with other linguistic features. Another simple yet powerful extension to search for word occurrences is searching for word pairs or triples, etc. We call this n-grams, where n is the number of words occurring together. Here we now start to uncover much more context about the words, given that we can see what typically comes before or after the words of interest. Term frequency, inverse document frequency. TF-IDF is a powerful technique to identify words of interest based on their occurrence, whilst also not being hindered by commonly occurring words that may not necessarily be of interest. Suppose we have a set of documents. For a single document, we may be interested in how often a particular word is mentioned. However, if this word is truly of importance to that specific document, then the expectation is that it should not be so frequent across other documents. For example, if we had documents reporting common vulnerabilities, for example CVEs, then a specific vulnerability such as Heartbleed may be highly mentioned in its respective document, but not mentioned in any others. This would mean that it should score highly than a word such as cyber, which whilst it may occur more frequently in the same document, it may also occur quite frequently across all documents. TF-IDF is calculated as follows. TF-T equals number of times T appears in a document divided by total number of terms in the document. IDF-T equals the log of total number of documents divided by the number of documents with T in. Let's consider our example using the words Heartbleed and cyber. Suppose Heartbleed occurs 10 times within a 100-word document. TF Heartbleed equals 10 divided by 100 equals 0.1. Suppose then we have 1000 documents and Heartbleed occurs in 10 of these. IDF Heartbleed equals log 1000 divided by 10 equals 2. Then TF IDF equals 0.1 times 2 equals 0.2. Suppose now we look at the word cyber and assume it occurs 30 times within the 100-word document. TF cyber equals 30 divided by 100 equals 0.3. But it also occurs in 750 of the 1000 documents. IDF cyber equals log 1000 divided by 750 equals 0.124. Then TF IDF equals 0.3 times 0.124 equals 0.0372. Here, Heartbleed has scored higher than cyber because in relation to the overall document set, it is deemed of greater significance. Recommender systems. How can a system learn to make recommendations? Recommender systems became popular through their use in market basket analysis, for example Tesco Clubcard, for predicting shopping habits and recommending products that would likely result in a purchase. However, they can be used in other applications to identify groupings of similarity and relationships between items, example words. Suppose we have 10 popular items and we have a record of 10 users as to whether they would buy that item or not, denoted by either a 1 or a 0. We can use this information to identify items that are purchased together or customers who are similar in their purchasing habits. If we have a new customer, we could initiate a cold profile simply by taking the average of all existing users. If we learnt that this new user then liked chicken, for example, we can update our recommendations by filtering so that we can average all users who also like chicken to obtain a revised prediction for this user. In this example, if Carl was a new customer, there would be a 90% probability of him buying pasta, since 9 out of the 10 existing customers do so already, and a 50% probability of him buying a pear, since 5 out of the 10 existing customers do so already. If we then observe that Kyle buys beef, for instance, he adds it to his basket, we can filter our dataset based on customers who also buy beef. This would then indicate a 100% probability of him also buying pasta, since all customers who have bought beef have also bought pasta, and a 75% probability of him buying a pear, since 3 of 4 customers who bought beef also bought a pear. Likewise, the probability of Kyle buying an apple goes from 40% to 0% because of him buying beef. There is a practical notebook available where you can explore this concept further. Now, this example being about items in a shopping basket, what if this was about words in a news article? We could learn to characterize topics such as sports, politics, entertainment and travel, and we could identify articles that appear similar to each other, essentially allowing us to cluster data, much like we have done earlier in this course. In a similar manner, we could also recommend the next word in a passage of text, much like how predictive text services function. Text models, therefore, can be used to both predict what will happen next, and also as a means of validating what has happened next, and whether this conforms to the expected model of behaviour. Spam detection. Another popular task for text analytics is identify whether an email is spam or not. As the use of email has exploded, so has the volume of spam email received. However, many providers have developed good models for detecting between genuine email and spam. So how do they work? Many systems use an approach known as naive Bayes, based on Bayes' theorem. The probability of spam given x equals the probability of x given spam times the probability of spam divided by the probability of x. This equation denotes conditional probabilities and can essentially be described as the following. The probability of spam given x. What is the probability of this email being spam given that it contains the word x? The probability of x given spam. What is the probability of the word x occurring given that this email is spam? Probability of spam. What is the probability of this email being spam? Probability of x. What is the probability of the word x occurring? Even with incomplete data, we can begin to populate values for this equation based on observations we have seen in our data, i.e. in the email set we already have. Over time, our probabilities can be updated so that our spam detection improves as new data is observed, essentially by clicking the junk option to inform the system of undetected cases. This is a powerful technique using Bayes. We cannot possibly have a model for all types of spam email, as there are infinite permutations of spam. However, conditional probabilities allow us to estimate this efficiently. An example of using naive Bayes for spam detection is available in the course notes. More on text analytics. As mentioned at the beginning of this section, there is a wealth of ongoing research and development in the area of text analytics that is increasingly useful for examining online materials and informing decisions about data, for example, social media posts, fake news, etc. Recurrent neural networks, RNN, are a special neural net architecture that work particularly well on text, as they are designed for sequential data. We can consider text to be sequential, as there is a specific order to words to make up a structured and meaningful sentence. For example, the cat sat on the, an RNN would likely predict the next word to be mat. In particular, long short-term memory, LSTM networks, are a form of RNN that are widely used which overcomes some of the early limitations in RNNs for how historical information is maintained over time. The main distinction between these methods compared to traditional neural networks is that RNN and LSTM take a sequence as an input, for example, a set of features with some inherent order, such as a time series, rather than a single observation of data, such as a set of features or a single image. We have shown methods that rely on feature representation, such as one-hot encoding of words to numerical vectors, essentially converting a list of words to a vector of zeros, where a 1 then represents the specific word. Whilst this can work in some cases, it can be constrained when a large word list is required, for example, the complete English language. Other language models exist. For example, word2vec has become adopted as a popular method for word embeddings. This essentially provides a model that can convert a given word to a vector representation in a more compact representation, i.e. an embedding, compared to one-hot encoding. This is similar in concept to PCA. It provides a dimensionality reduction on the data to present a meaningful yet compact representation. Word2vec can be used to define a continuous bag of words where, given a set of words, what one word would fit within the set. Similarly, it can also be used to define skipgrams, where, given a single word, what set of words would fit within this. We can see that these two methods are the inverse of each other. Extensions to the word2vec model have been proposed, such as Doc2vec, which generates vectors to summarize complete documents based on the word2vec model, offering a model compact representation for larger document analysis tasks. In recent years, there has been a great interest in language models and developing automated models for tasks such as chatbots and image captioning. If we consider a single word as a vector, a simple model could be considered as a vec-to-vec model, for example, word translation. This essentially means we've got an input vector going into a model to give an output vector. In our earlier example, we may have a sequence of words that then predict a single output word. For example, predictive text, which we could consider as seq-to-vec, sequence to vector. By extension, we may then also be interested in models that adopt vec-to-seq, a single input mapping to a sequential output, and seek-to-seq, a sequential input mapping to a sequential output. Language translation could be considered as seek-to-seq, since we may have a variable length input and a variable length output. Another good example would be for a conversational agent, such as a chatbot, since the length of the input, i.e. the number of words in a question, may vary in length each time, and likewise the length of the output, i.e. the answer given by the system, may also be variable length. Text analytics and language models are perhaps the most groundbreaking area of research in delivering artificial intelligence. Generative Pre-trained Transformer 3, known as GPT-3, was released in 2020 by OpenAI in their research paper, Language Models Are Few-Shot Learners. It uses 175 billion parameters in their learning model and achieves near-human accuracy. Whilst it can do traditional text tasks like sentence completion, they demonstrate its effectiveness for truly understanding text, such as executing commands as described by a human. From building applications based on a written description, smart assistants that can recognize tasks and provide recommendation, and many other examples that are available to see online. There are 2 videos in particular that describe just some of the possible applications, by 2-minute papers and by half ideas. With the internet serving to inform the model and compute power ever increasing, there really is a great wealth of potential to be explored here.